Hey, this is Tim McLaren. I'm Scripps Mercy Hospital intern, and I did some research a couple of years ago at UCSD where I started to come in contact with um, sources of big data, and I started to appreciate how AI is going to be a critical part of medicine moving forward. And it left me with this big question in my mind of, will I have a job? Being a physician is cognitive labor, and that's what AI is great at doing. So this what I'm about to take you through is kind of my journey. It disturbed me first, and then inspired me. And so let's go through it. We're going to start. I'm just going to tell you about some technologies that will sort of underlie the future of precision medicine. I don't have any disclosures. I wish I did. I'm going to be talking about some companies today, just as examples. I don't have any financial interests in those companies, though. So this is how I see the current situation in medicine. We have people who are not well, and we have a variety of treatment options. For each person, certain treatments will be more effective than others. Some treatments may even be completely ineffective, and some could be harmful. We're often left to guess which treatment will be best. So we do our best. We have guidelines to help us based on sort of population averages, but we end up performing many ineffective treatments on those who have access to care, while resource limitations leave many others without any treatments at all. But what if we knew from the very beginning what treatments will be most effective for each person? How would that look? In an ideal world, each person would receive the most effective treatment available as their first treatment. We would not put our patients through unnecessary, ineffective treatments, and we would conserve our healthcare resources so that they can be shared more evenly among the entire population. That's the hope of precision medicine. So what makes the fundamental difference between so-called precision medicine and the way we've always done things? So the goal of precision medicine is to match patients with treatments that will make them well. But isn't that what we've always tried to do? So the difference comes in how we approach the goal. In its ideal form, precision medicine characterizes each patient well enough to understand the causes of disease with molecular specificity. Treatments are targeted to interrupt pathologic processes at points where they will be most effective with the least side effects. Again, this is the approach we've tried to take, and we have made some progress. The problem is that we have largely lacked the tools to characterize patients with molecular level specificity. So we do not understand the exact pathogenesis of some of the most important diseases of our time, cardiovascular disease, diabetes, cancer, etc. And we don't know why certain subsets of the population respond better to certain treatments. We've just been relying basically on a gross characterization and then guideline-directed therapy based on population averages. So the first building block of precision medicine then is precise scalable analytics. And I think the place where our minds tend to go when we first think of precision medicine is genomics. And I think rightly so. I mean, this is the underlying code of A's, T's, C's, and G's that somehow take us from being single-celled organisms all the way up through maturity and through all the stages of development throughout our lives. It underlies our biology. It's a critical piece. And I think that's pretty well understood. But what surprised me was the cost of human genome sequencing has fallen precipitously since it started. Back 20 years ago, it was $100 million to sequence a human genome. And I just had a couple of friends tell me recently they'd had their whole genome sequenced. I'm not talking about just a few SNPs like you get from maybe 23andMe or Ancestry.com, those kinds of companies. While those are great, my friends had their entire genome sequenced, every single A, C, T, and G sequenced. And it turns out that you can actually do this now for under $1,000. This company, Veritas, is advertising for $600 to sequence your whole genome. And just to put that in perspective, this is the, if you look at the charge master for the Scripps Health system, this is where human genome sequencing would fall. If we put it on that continuum of charges. Just to give you a sense of perspective, here are a few things that are more expensive than human genome sequencing. So clearing out the outer ear canal, arterial puncture, inserting a bladder catheter, checking to see if you have the flu. We're using a PCR. These are all things that in theory would be more expensive than whole genome sequencing. And then without even using AI or the methods and techniques I'm going to touch on later in this talk, we already can see associations between many different genes and susceptibility to many different disease states. Cancer, cardiovascular disease, connective tissue diseases, malignant hyperthermia, susceptibility, and the list goes on and on and on. So we'll add genomics as the first building block in our precision medicine toolkit. But in fact, actually, decades of epidemiologic research have shown that the majority of population attributable risk of human disease is not purely genetic in etiology. It actually comes from everything we experience: our endogenous physiology, the microbes that inhabit our guts, everything we eat, drink, and breathe, and the drugs we take. The problem is it has been notoriously difficult to measure these things. Now, these experiences exert their influence, generally speaking, by the introduction of small molecules into the bloodstream, which then go on to exert their effects in three main ways. They participate in chemical reactions, cell signaling, and metabolic pathways. So we can use these small molecules as more specific measures of our experiences, and we can associate them with outcomes of health and disease to find out what matters, and perhaps why. This is an example of a mass spectrum. Mass spectrometry is currently the best way that we have to survey the thousands of small molecules that flow through our blood. And you can see that there are many different families of molecules in blood. So, in the lab where I worked at UCSD, we developed methods to automate the mass spectrometry-based surveying of human blood. And we applied our methods to a cohort of over 1,000 samples. And our goal was to really reduce the time and expense that it takes to do this kind of study. And typically it was on the order of 100 minutes per sample. We were able to get that down to about 1 minute per sample. And so within a day, we were able to assay the serum of over 1,000 participants. This is the San Diego population study. And the outcomes in this study are a lot of cardiovascular disease outcomes. And so we applied our metabolomics assay, and we found that there were a couple of molecules that associated very strongly with cardiovascular disease. This is a modified Manhattan plot with the adjusted log P for association with cardiovascular disease. And so basically, the higher you are on this plot, the stronger your statistical power. And the thing that really interested us with these two molecules was that it turned out that they actually correlated inversely with the number of cardiovascular disease events. So the healthiest people actually had the highest levels of these molecules in their blood. And the more cardiovascular events a person had, the lower the levels got, which was really intriguing because if it's a deficiency in these molecules that leads to disease, that's very treatable. You just just add it back in, you just supplement it, right? So we've seen an association between an outcome and a couple of molecules in our blood, and that association is consistent with a protective role for these molecules, but that doesn't imply causation. However, if these molecules do cause protection, then they might also associate with protection against some state which precedes cardiovascular disease. And in fact, we do see a strong inverse association with 3 different markers of inflammation. These data certainly don't prove anything, but they begin to focus a mechanistic hypothesis. Now, let's step back for a minute. We've taken a comprehensive view of the internal milieu. We have found associations with clinical outcomes, and we've started to form a mechanistic hypothesis. But let's go further back in the chain. If the decline in these molecules is not just the result of cardiovascular events, are there actually environmental factors that could modulate serum levels of biologically important molecules such as this? By linking big orthogonal data sets, we will be able to understand the rich web of interactions that influence our health. So we'll add metabolomics to our toolkit, the study of the small molecules in our blood. Now, there was something that really bothered me coming out of these couple of years of research, and that was when I had my data in front of me. I had thousands of patients, and in each of those patients, I had thousands of molecules in their blood, and I knew I had in front of me human physiology playing out right in front of me. To my limited human brain, it meant nothing. It was just a bunch of numbers on a page. It was just a bunch of little lines on a graph, but it didn't really mean anything to my human brain. It was way too much complexity for me to deal with, which is why I took the reductionist view and just looked at individual molecules and how they correlated with individual factors, but I couldn't shake the feeling that I was missing the forest for the trees. So that's our challenge, drawing meaning out of such massive, beautiful data sets. And so traditionally, when a physician meets a patient, the way that they try to come to understand that patient is they will talk to the patient, get a history, do a physical exam, we'll do some imaging and some labs, and then we'll try to summarize those things in the medical record as best we can with the time we have available, which usually isn't much. And you start to come out looking kind of like this. And if you're wondering why machine learning and AI hasn't really made a splash in the world of medicine yet, it's because this is what it's working with. This is what's on the computer. It doesn't know you very well. Think about this. If a picture says 1,000 words, how much does a genome today? Or what about the 2,000 to 40,000 molecules that are floating around in your blood? How much do they say about you? So when we start to layer in these big, beautiful, rich data sets, the version of you that's on the computer starts to become much more real to life and more nuanced than anybody could express in words. And what's more, these technologies are inherently digital, so we can place all of your data into a database alongside thousands or even millions of other people to start to tease out the complex hierarchy of patterns that exist in states of health and disease. But again, we're faced with sheer size of the data. So the genome's 3 billion base pairs. The microbiome is 10,000 species in your gut, inhabit your gut. In the serum metabolome, you have anywhere from 2 to 40,000 different chemicals that flow through our bloodstreams. And then, of course, in the clinical, you could describe anything in natural language. And what's more, we don't just get these data once. Many of these data can be collected multiple times throughout a person's lifetime. There's a tremendous amount of data, and our human brains are completely inadequate to comprehend the bigger picture and see the full web of interactions among these. But let's just think about what do we actually want from this? For me, I would like to see a description of the pathology, and I'd like to see treatment recommendations, particularly the treatment recommendations. And that might look something like this. If a machine were to try to put this out in a human understandable form, this web of interaction. And then the key there is, of course, the treatment recommendation. So how do we get there? This is the artificial intelligence in its early days has its roots in the study of human intelligence and how our brains work. And a retina is represented here in these black lines. Retina is a good sort of basic understanding of how neurons work. And so we'll use that as our example. So here you have a dot and a line, right? And let's say the light comes and hits the dot and then bounces off and goes to the retina. And your retina has this little neuron there that says, I recognize my pattern. My pattern is a point, and I recognize I've been activated. And so we could then have more light come and hit the line here. The rays of light bounce off and come to your retina, and then each of these little neurons in the retina says, I see a point, I see a point, I see a point, I see a point. And so you have a bunch of points, right? Well, if those points happen to be all next to each other, there may be some higher order neuron that is receiving input from all of those points. And it recognizes when those go all fire off at the same time, it says, oh, I see my pattern. My pattern is a line. And it says, and so it activates that neuron. And you could have a higher order neuron than that even that recognizes this repeating visual pattern of point line, right? And then if you happen to know the English language or any other language that uses this character, you may recognize a more abstract, this may, activate a neuron, a higher order neuron, that's more abstract, this concept of the letter I. And that could be activated also by an auditory pattern. If I said the word I might also activate the same letter I neuron or family of neurons. So let's keep that basic idea and moving forward. So if I were to take serum metabolome from multiple people and then ask this computer algorithm to find patterns for me that start to emerge as you look from one person to the next. Are there certain patterns that emerge? And so it can start to tease out this complex hierarchy of patterns that exist in biological data. And then what if we take the metabolome data, all these small molecules, and what if we associate then the electronic medical record data and say, okay, well, these people had cardiovascular disease, actually. These people didn't. Then we can start to recognize that there are certain patterns that associate with an atherogenic state for people who are developing atherosclerosis. So that's just an example to show you how we can apply pattern recognition in its most basic form, and then it builds up this hierarchy of patterns until you start to be able to make strong predictions. And so this is another critical building block of precision medicine. As I said earlier, my human brain is just completely unfitted to the task of comprehending these massive data sets in their entirety. I can do the reductionist approach. I can take one molecule at a time, but I totally miss the forest for the trees. Machine learning doesn't. So we'll add machine learning and computational power to our building blocks. So when I give this talk, I've given it to internal medicine physicians, and I've given it to cardiologists, and I asked this question of them: ask if I want to live 100 years, or if I want to, let's say in other scenarios, if I want to be really buff this summer, if I really want to beef up and get strong this summer and look great in a swimming suit, what's the best diet for me? What should I do? And the internal medicine docs were kind of favoring towards the myplate.org, or down in the left-hand corner here, which replaced the old food guide pyramid. Interestingly, though, the cardiologists were pretty well split among all the different groups here, which is kind of interesting, right? These professionals, there's no consensus about like, okay, well, this is the best diet for you for any given goal. Why is that? Why is it that with all this knowledge and training, we don't have one clear answer? So this is Iran Elinav and Iran Siegel, and they formed the Personalized Nutrition Project because they were interested in this question. And an early finding that they had that really framed their thinking on this was you can give the same person bread on 2 different days, and the level of glucose, the rise in their glucose in their bloodstream after they eat that piece of bread is going to be pretty similar from one day to the next. As you can see here on this graph, you've got each color represents an individual person, and then the 2 different lines are 2 different days when they've eaten the same exact bread. But what's really fascinating is that it's very different from person to person. Even though it's very reproducible within one person eating the same meal, from one person to the next, if I eat a piece of bread, it's going to react very differently than if you eat a piece of bread. My glucose spike is going to be very different. So they were really curious what accounts for this difference, and they did this wonderful project where they took 800 people, sequenced their microbiome, the microbes that inhabit their guts, and then they did blood tests and questionnaires and anthropomorphics. They followed these people for a week using continuous glucose monitoring, and they had them take meticulous notes of everything they ate, their sleep, activity, and they had them eat standardized meals as well for control. And they took all these data and they allowed machine learning algorithms to learn the patterns within the data. And then their goal was to be able to predict how any given meal would affect a person's blood glucose, how much it would spike their blood glucose. And so they developed this algorithm that could do that based on the gut microbiome and some of these other initial profiling data. And then they tested that on a validation cohort of another 100 people. Now, using traditional methods of trying to predict how much a given meal is going to spike your glucose, we typically think of like carb counting or calorie counting. Those are common ways of people doing it. If you look at how well your carbs can actually predict how much your blood glucose is going to spike after a meal, it's not a good predictor. So this R value, if you have an R of 1, that's perfect correlation, perfect predictive ability. R of 0.038, you can see it's kind of all over the board. And same with calories. Now, what's crazy about this is that when they used their machine learning algorithm to try to predict these glucose responses to meals, they found that they could do so with great accuracy. this is based on microbiome data. So it's interesting that the gut microbiome, the microbes that inhabit our guts, really shape the way we respond to our food. Fascinating. But look at this. So the R value on this is 0.7. Remember I said an R value of 1 would be a perfect predictive power. 0.7, that's not that great, right? Well, actually, if you look at the intra-person variability, so this is same person eating same meal on 2 different days, it's only going to have an R of about 0.77, right? So that's the R that they saw in the validation cohort, the correlation coefficient that they saw in the validation cohort, is actually nearing sort of the upper limit of what you could theoretically predict. So this is actually a very strong predictive power. So the company went on to, or I'm sorry, the institute went on to license this machine learning algorithm to a company that they'll sequence your microbiome for you, and they'll give you access to this app after they sequence your microbiome that you can type in whatever food you plan on eating, and it'll give you a prediction, a score of 1 to 10 of how good or bad that meal is going to be for you in terms of your glucose spike. So for example, this homemade chili meal, it's got an 8.5 score, which is very good. The 10 is good. It means it's not going to spike your glucose. Your glucose is going to stay pretty level with this. And a 1 is really bad. It's predicted to really spike your glucose badly. And then they also give you meals that are suggested for you. I tried it out. I went in, I got a continuous glucose monitor from a friend, and I wore it for a week, and I meticulously recorded my meals, and I sequenced my microbiome and got predictions from this company about how each meal would spike my glucose. These are my day 2 scores. Day 2 is the company, and these are my day 2 scores on the bottom here for each of my meals. And so we'll take the first meal, for example, this Cheerios and oat milk. It was predicted with the low day 2 score, it was predicted to spike my glucose pretty well. And we can see it did have a pretty big spike, pretty sharp spike. And the pattern you see here is there's the initial glucose spike, and then my pancreas puts out a big bolus of insulin, and so my glucose then drops, and then I'm still digesting, so my glucose goes back up again, and then my insulin puts out another bolus of insulin, and my glucose drops, and so I have the spike, drop, spike, drop, spike, drop kind of pattern that happens, and happens with pretty much every meal. But anyway, so the first meal you can see has a pretty good spike. Second meal, the cheese pizza and lettuce was about 5.1, so it's kind of middle of the road. You can see it's a wider spike. It's certainly looks different than the Cheerios and oat milk. And the best score of the day, the 8.8, was actually a caveman almond coconut dark chocolate bar. Who would have thought I would have it would not spike my glucose much? But actually it performed pretty well, and that lined up pretty well with the day 2 score. And then the last meal of the day, butternut squash soup, brown rice, pork, milk, Kirkland nut / chocolate bar. I really thought this was going to be like a good meal for me. It seemed like a very healthy kind of meal. Day 2 predicts actually that it's not a good meal for me. And if you look at my glucose spike, that is definitely the biggest glucose spike of the day. So I'm still working on the sort of quantifying how well all of the spikes correlated with my day 2 scores throughout the week, but this just gives you a sort of a nice initial visual estimate of how things look. So it turns out the best meal for me is one based on my own data, and that's really how medicine is going to be in the future. It's not going to be based on population averages and guidelines. It's going to be based on your data. So we're going to add now microbiome sequencing. And in order to make these kinds of analyses work, you really need participation from a lot of other people. And you need a place to store all those data, because you need to be able to put these big orthogonal data sets into the same database and have lots and lots of participants for these machine learning algorithms to learn from. So you can tease out this complex hierarchy of patterns that exist in biological data. And I'm going to add a couple of other things. So activity monitoring, whether it's a continuous glucose monitor or a Fitbit or an Apple Watch or one of these other things that can track your heart rate and your step count and these other and your sleep, things like that. It's going to be an important part of precision medicine as well. And then up next to the blood vial here, I've added an antibody representing the immune repertoire sequencing, which I won't get into today, but I think is going to be another critical piece here. So these building blocks are actually already falling into place. These are a lot closer to ready for prime time than I think most of us really appreciate. But recognizing that, back in 2015, President Obama, in his State of the Union address, announced the Precision Medicine Initiative. And this Precision Medicine Initiative ended up developing this really audacious research program, which is it's exactly what we need. They're going to take 1 million people, follow them for 10 years, and they're going to collect blood and urine and various biospecimens from these people. And this is going to give us this is going to get us over the hump, right? So in order to have power in your predictions, you need to base those predictions on a very large number of people that have been sequenced or had their metabolome measured or whatever. But how do you pay for all those sequencing and all that? So this is the government recognized they needed to step in, provide the initial massive data set that makes it useful for us to sequence our microbiome and to measure the serum metabolome and to sequence our genomes. Because once that data set is there, then when I go to the hospital and I get my genome sequenced, now there's a whole cohort of people against which my genome can be compared to make predictions, right? So this is a critical program to get us over that initial hump to the point where it becomes useful for each of us to have these kind of big data sources drawn from us. And so they'll also take physical measurements, and people take online surveys, and then they'll connect this with the electronic health record data, which is also critical. So we've seen now an example of how we can take two large data sets and we can ask machine learning to find patterns in them. And then using those patterns, we can go back down the tree and make predictions. So in our example earlier, we used microbiome, patterns in the microbiome data, and patterns in how, what people are eating and how that affected their postprandial glucose responses or their glucose spikes. And we used those patterns to then make predictions. So then we could use the microbiome to predict how any given food is going to affect a person's blood glucose level, even if they've never eaten that food before. And so this becomes a really powerful thing when you connect these orthogonal data sets. And so the next steps are going to be adding in genome data and metabolome data and everything from our electronic medical records. And so these will start to form the core of precision medicine when we get all of these data alongside each other and then apply machine learning to all of them. But this is, just to wrap up, this is my vision of how things may go in the future. It's one version of how things may look. So you go to the clinic, you give samples of your blood, urine, and feces. Then this is just, a future, this is how it's going to look when you go to your doctor. You have samples of your blood, urine, and feces. Automated laboratory systems perform deep sequencing on your genome to determine your genetic background and on your lymphocytes to determine your current adaptive immune sensitivities. They sequence the microbes in your stool to determine the composition of your microbiome. They measure the thousands of small molecules in your blood to characterize all of your exposures, to see how life has been treating your body. And all of these data are placed alongside data from millions of other people. In a centralized database, where machine learning algorithms reconstruct the complex hierarchy of patterns that make your body what it is. Back at the bedside, your physician enters your chief complaint into the system, and it responds with a specific explanation of what is happening inside of you, based on your own data. If additional data are required to make a definitive diagnosis, the system knows which questions to ask and which tests to perform. Then, just like your GPS, the system takes your personal data and plots the most effective course of treatment to return you to optimum health. You and your physician discuss it. If some part of the treatment plan is not acceptable to you, then your physician tells the system to reroute for the next best course. An app on your phone provides reminders to help you follow your treatment plan, and it checks in to see how well you're doing. Your physician keeps an eye on your responses and follows up as needed. So this is one version of how things may look in an era of precision medicine. Just got to acknowledge some wonderful people in my life. So Dr. Mohit Jain and Jeremy Watrous are wonderful scientists at the University of California, San Diego. I was privileged to work with them on the metabolomics work that I was presenting here. They're brilliant. They've taught me a lot. And they taught me how to think about science too. Karnoff Cardiovascular Research Foundation funded my research and provided some key mentorship throughout my career. And the Scripps Health System is where I work now. They're my new playground, and love it. Wonderful place. Great people. Great environment. Great patients. And this is Eric Topol on the bottom here. He's the founder and director of the Scripps Translational Research Institute. In 2016, he was awarded a $207 million grant from the NIH to lead a significant part of the Precision Medicine Initiative, the All of Us program. And he's given lots of talks that I've been watching, and he was the one that clued me into the Day 2 app and these microbiome predictions of predicting blood glucose samples. He doesn't know I exist yet, but he's been a shining light. And then, of course, on the right here, we have my wife and daughter and Falcor the luck dragon. And my wife and I often talk science. She's a scientist too, and so she's been a great support to me. A few great reads here, things that I've found very useful. We'll start on the bottom right. How to Create a Mind by Ray Kurzweil. This is a really good introduction to sort of conceptually thinking about how machine learning and artificial intelligence works in general. AI Superpowers by Kai-Fu Lee really addresses this big question of what will I do when AI really comes into its own, taking the cognitive labor of the world. What will be my place in that world? And then Deep Medicine by Eric Topol talks about a lot of the great applications for how AI is making inroads into medicine and what that world will look like in medicine. And then the All of Us research program, this isn't really a reference to go read. This is more of a reference to go do. Join All of Us. You can join it. Anyone can here in the U.S. I'm a member. I'm a participant in this study myself. It's especially looking for people who are underrepresented, groups that are underrepresented classically in research studies. So, you're not the typical Caucasian male Framingham cohort, anything other than that, they really need you in that study so that we can understand how your genetic background and your culture affects health and disease in your body. Caucasian males, don't feel bad. You can still join it too. But really everyone else, if you're not of that demographic, we need you. So please join. And then I'll just end with a question that I get sometimes, and that has really been a big one on my mind. And that is, what will I do in this future of AI? Kai-Fu Lee does a great job of sort of breaking this down for us. So let's first start on the left, cognitive tasks. Basically, the idea is you don't want to stake your career on things that AI is going to come along and do much better than you do. So you want to really build your expertise in areas where AI is not going to be strong. And so on the vertical axis, we have social and asocial. So the more social your job is, the harder it is for AI to do that thing. The less social, easier it is for AI to do it. And then on the horizontal axis, we have optimization based. It's easy for AI to do optimization based cognitive tasks, whereas creative and strategic sort of tasks are very difficult for AI. And so you get some examples of each type of worker or career field in each of these corners here. And then in physical tasks, similarly, social physical tasks, very difficult for AI. Asocial physical tasks, easy for AI. And then on the horizontal axis, unstructured environments are difficult for AI to navigate through. Very structured environments, on the other hand, are very easy for AI to navigate through. They navigate, or they thrive there. And then tasks that require high dexterity, very difficult for AI to accomplish. Things that require low dexterity, easy for AI, right? And that may change in the future, but that's kind of where it is now. So just the dexterity, but I think the rest of it applies. The social or asocial, and the structured or unstructured environment, and the creative strategic thinking. I think all of that will probably continue to apply as we move forward, even as technology advances. I think those will continue to be hard for AI. And so you've got some examples of physical tasks that AI would be particularly good and bad at doing. So anyway, I hope you have enjoyed this and perhaps gleaned something from it. I've certainly had a wonderful time thinking about these things and exploring these worlds, and I look forward to continuing into this future.